Alright, well hello everybody. Here we have a simple mass spring dashpot system, and in this case the mass spring dashpot rides along a smooth inclined surface. And we're told that this block itself is connected to ground by two springs of stiffness 4K and K respectively, and that there's a dashpot of damping constant C. And what we're asked to find is the value of the damping constant such that the system has 50% of critical damping, and we're given some numerical values for K and M to help us out. So to start this problem, as we do in most, we can go ahead and start by sketching a free body diagram for this system. And in fact, to be honest with you, most of the complexity of all of these problems are in drawing this free body diagram and correctly constructing the equation of motion. In this case, we're told x is positive down the slope, and so I'll note that my mass times acceleration will be positive in that direction. And then I'll note that if x is displacing positive downwards, I'll have opposing spring force of magnitude kx, an opposing spring force of magnitude 4kx, and an opposing dashpot force of magnitude cx dot. In addition to these, I'll have a normal force which is perpendicular to the slope, and of course I'll have weight which is acting down. And probably just kind of for the sake of helping us out later, I'll note that this interior angle here with respect to the normal force is given by the angle theta, where theta is the value given in the problem. So next thing I want to do is construct an equation of motion here. So if I do that, I can go ahead and sum forces in the x direction and set that equal to m times x double dot. X, of course, again being positive down the slope. And if I do that, I'm going to have minus kx minus 4kx minus cx dot plus mg times the sine of the angle theta is going to equal m times x double dot. I can then write this problem into standard form, and that's going to give me that m times x double dot plus c times x dot plus 5 times k times x is equal to mg times the sine of the angle theta. Now, because I'm asked for something with respect to critical damping, I need to re-express this problem in terms of a damping ratio and natural frequency. In that regard, I'm going to mass normalize the equation of motion, which I can designate as such here. And if I do that, I'm going to end up with x double dot plus c over m times x dot plus 5k over m times x is equal to g times the sine of the angle theta. At this juncture, I'd ask you to remind yourself that by definition, 2 times zeta times omega n is equal to c over m, and omega n squared is going to equal 5k over m. What does this mean? Well, if we're asked to find the damping constant such that the system has 50% of critical damping, I can set zeta equal to 0.5, which is going to give me the result that omega n is equal to c over m. If I substitute this in, that means that c over m is going to equal the square root of 5k over m, which means that c has to equal m times the square root of 5k divided by m. And that'll give us the final answer for the system. The interesting thing here to note is that really the angle of inclination has zero effect on this problem from a damping point of view. It's an interesting result and something to keep in mind as you move forward in industry or academia. Take care, everybody.